here. So, what page is that, please?
17. No, 35.
Okay, so we're going to have a look at number 5. 2 open ordering pipes of length 50 and 51 give beats of frequency 6 Hz when sounding their fundamental notes together. Neglecting error corrections, what value does this give for the velocity of air in sound? So some people got 306, some people got 303, some people got 24. I'm actually very curious to how you got 24. Let's see what you did.
I find the lambda of 50 and the lambda of 51. I got and then
48.
V equals to lambda.
Yeah,
What's
also
together?
it's different messages and different lambdas. So it means that none of those methods is correct.
And I need to comment on the
Second.
It says there's 2 5, 50 centimeter and 51 centimeter.
Yes.
I convert the centimeter to meter and I use the formula it gives us lambda equals to length equals to lambda of what?
It's not that one there, I'm sorry. Yeah. It's, let's have a look here. I'll show you where it is. If you want to have a look at page 26.
Do you know what 50 is correct?
Guys, can you look at 26 here? So it says at the top of 26 under vibration, the fixed ends must be displayed. Okay, if the string is plucked in the middle, the simplest mode of vibration occurs, A being a displacement antinode. This vibration creates a fundamental note of frequency and L over 2. So if you have a look,
So
I
the
don't
next
have the,
formula where F equals V over 2L is 1
and where is it? Is that on that page, did you say?
Yeah, the next.
F equals V over 2L. But you also used V equals F lambda.
Yeah.
But that's 0.51, not 51.
Nope. It's a good 51 centimeters.
Yeah, 0.51 meters.
Oh.
Yeah, so that's not right then. So we'll have a look at the way you did it then. I think will be it. Well, you didn't get an answer for 5. No answer? Impossible?
Yeah, it's impossible.
Impossibly difficult. Okay, let's have a look at it. So number 5, you have 2 pipes. This one here is 50 centimeters, so 0.5. And this one here is 51 centimeters. So far okay? Now, you're right, you use the formula V equals F lambda, wasn't it? F equals V over 2L. But you use it for both.
Yeah,
And you add both together.
equals 6.
Okay. Just give me a minute, please, and I'll do it. Well, did you get all those finished? Did you finish all the questions except for 5?
Yeah.
Okay.
So what we can do next time?
Do it when?
Next time. Next lesson.
I don't know. I think that might be better for me.
And today I can concentrate on the next order.
We can just stick together.
No, we can't.
Yeah, you can take your time, Mr. Steven.
Just give me a moment, please. Okay. Well, I'll first draw it anyways. So what's happening here, there's a note inside of this. Do you remember yesterday we were talking about harmonics?
Yeah.
Do you remember harmonics? So harmonics is how many
Nodes.
No.
Oh no, antinodes.
antinodes, isn't it? How many antinodes are in this one? One. When there's one antinode inside it, there's a special word for that. One antinode. We call this the fundamental frequency. Is that the word they use in the question? I think so. Fundamental.
Fundamental node.
What's wrong?
According to the notes that we took last time, harmonic means how many notes, not anti-notes.
Sorry, it's how many nodes, is it?
Yeah.
Is that what I said last time?
Yeah.
Yeah.
Alright, so sorry, not antinodes. How many nodes here? Not counting the ends. So 0 nodes is fundamental. In other words, the fundamental is the one that just has half a wave. It's the first one. Okay. Right. In the other one, it's the same. Of course, that one is bigger, isn't it? Right?
Yeah.
Because it's still one one fundamental, but it's a longer pipe. Yeah. Okay, so what formulas do we have? We have, yeah, well first let me just write the V1 down. What's the V1? V equals F lambda. Now, do we know the lambda here?
We can
Yeah.
find it.
That's what we have to find.
That's what we have to find. The lambda?
Yeah, four.
Oh, well, we do know the lambda because it's just going to be twice this number. And then what's the lambda here? 1.02.
Twice or four. Four times.
Now, in this one now, it's twice, not 4, because you're not trying to make the pipe shake.
So what does it do to the pipe?
So the key word in the question is fundamental, which means like the 0 harmonic, before the first harmonic we did yesterday. Do you remember we did harmonics yesterday?
Yeah.
So we had 1 harmonic, 2 harmonic, and I showed you on the video here what that looks like. And it's how many nodes there are. So this is called the fundamental frequency.
But what is that divided by 2?
Oh, well, that's half a wave. Isn't it?
Yeah.
It goes up, there's no minimum, it's just the first half of the wave, isn't it? So, if I want the wavelength, it should be twice the length of the pipe. Shouldn't it?
Yeah.
Yeah. So, what are the two wavelengths? So, this one here has lambda of 1,
Yeah.
and this one here,
1.02.
1.02. Okay. Now, if you were to use each of those to get the V, in the first formula, you would get V, speed of sound, equals frequency, which we don't know. Well, that's, they said when it's combined together, isn't it? It's 6. But we don't know what it is before they come together. It does say when the sounds come together, is it 6?
Yes.
And gives beats of frequency 6 when sounding their fundamental notes together. So we don't actually know if it's 6 at the beginning. So I don't know the lambda. Oh, sorry, I do know the lambda, I don't know the F. So that's 1. And then here I have V equals F lambda. So V equals F multiply 1.02. And I suppose I should really say F2 and F1 then. but their speed is the same. But the problem here is this. Really, we have 3 unknowns, isn't that right? F1, F2 and V. So we need another equation to make this solvable. And we haven't used the fact yet that when they come together, they make a frequency of 6. Yeah?
Oh, yeah.
We haven't used that yet, have we?
No.
So how can we represent that piece of information, that when they come together, they have a frequency of 6?
F1 plus F2 equals this.
No. Well, this is the thing. Do we think frequency adds or not? What do we think?
Yes.
The frequency adds.
Yeah, like if something has frequency F1 and this cell has frequency F2 and they come together, what's their combined frequency?
Oh no.
They don't add together.
They do.
They do.
They do. They do.
Do they?
I think it seems logical.
I knew that amplitude adds together.
Amplitude adds together. But let me give you an example. Like, if I'm speaking with frequency F and someone else is speaking with the same frequency. In fact, if I have 2 speakers with the same sound and they have the same amplitude, then the weight in the middle, the amplitude will be twice as big, right?
Let's take 2 circles. They make, I don't know, 2 spins in a second. So together they make 4 spins.
No, but
Frequency is 4.
But think about it like this. If you have 2 speakers and they're playing the exact same thing, yes, when they come together, the amplitude is twice as big. So the amplitude adds together. But when they come together, they still sound the same, it's just louder. They still have the same frequency.
We get the answer. The 2 frequencies.
F1 plus F2 equals 6.
Yeah.
Together with these 2,
Yeah. V over lambda plus V over lambda equals 6.
I don't know.
Oh yeah.
I just did that.
And it works.
Yeah, 36.
I'm shocked, and I don't believe it. But I'm going to continue and see if it happens. It's not that I don't trust you, Joshua, but someone with glasses that geeky has to be right. You know geeky? That's what? All right. Your teacher's what? No, repeat. What?
Bully.
No, he's not bully. He's a... Anyways, can you solve these 3, please? And see what you get when you solve them.
What do you get?
806.
I'm not happy with that, but oh well. I know, but
the frequency is the same for Wilson for anything.
yeah, but you do understand my example with the 2 speakers, though.
What is frequency in the sound? What does it represent?
1 over the time, so it's related to how quick it's moving. But I suppose these 2 are working together. It's not like 2 speakers.
In the second, right?
Yeah.
Frequency. So one speaker, let's say 2 wavelengths, and another one 2. In total, they have 4 wavelengths.
Need to picture that. This one's coming out F1. That one's coming out F2. I think there's something in semester 2 we can use in maths that might help. What did you get for F1, F2 and V?
I just get the V.
Oh, isn't that what we wanted, V?
Yeah.
Yeah, what you get for V?
306.
What is it?
306.
Okay, and the F1? I'd just like to know what they are. I'm curious.
One of them is 306, and another one,
For F1?
Yeah.
and another one is 312.12.
They're 65.
Oh, sorry.
300?
Oh, yeah.
300 hertz. And then here? 306 hertz. And then here? Meters per second. I am not happy with the F1 plus the F2. I think I do wonder if you'd still get the same answer if you had F2 minus F1 equals 6. I'm going to check it in Derive. I think a graph would really help here. See, the reason I'm talking about the difference here, I'll draw it here. Can you read out the first equation, please? What was it? V equals F1, which I'll just call X, multiply 1. And the other one, V equals Y multiply 1.02. It's just minus, it's the wrong way around. If I do X minus Y, one, 2, and 6. Yeah. And now you see, I wasn't convinced about the adding together the frequency. I think it should be subtracted. And this is the reason why. If you look,
One is bigger than another.
yeah, well, if you look here, here is sine X. Now, how long, if we make, for example, here amplitude and here time, what's the time for this? For one cycle? Now look at the graph. How, what is it? Yeah, about 6.28, isn't it? Yep. Now, that's right, I can't trust you anymore for calculator answers because you're always giving me the... Anyways, I got it, it doesn't matter. It's not F1 plus F2, I don't think. Can you look up, please? There's sine X. What's its period? It's 6.28. So what's its frequency? 1 over 6.28. Yes? Now, if you look at this graph, cos X, what's its frequency? It's the same, isn't it? So if I add them together now, in the black one, what's the black one's frequency? Goes up, down, and back up. What's its frequency? It's the same, isn't it?
Yeah.
So the frequencies did not add. What's more important, I think, is the difference in the frequencies. So for example, here, let's say you have sine 2x, and then let's say sine 3x. what's the frequency? Well, let's just do what's the period here. It's 3.14. And what's the period here? It's smaller, isn't it? If I add them together, I get this. So it goes up, down, up there. But no, that's not even finished. Then down and then back up. So there's one cycle. So one cycle is not 3.14. You see? And it's not what the other one was. It's somewhere in between the two when they combine together. So in other words, my point is it's not how big each one are, but how different they are that determines the frequency of what's produced. So what you've learned is that when combining waves, their frequency is not a function of their addition, rather it's a function of their difference. Because if they were the same, they were equal, then what is their difference? Zero. And they would produce a wave of the same frequency, but just maybe a different amplitude. Okay? So I'm glad we did this one. I think it's something valuable learned here. When combining waves, it's their difference that counts, not their addition. Can you make note of that? So when waves combine, their resultant frequency depends on the difference of the original frequency, not the addition, the difference. When I'm trying my best to think of the past exam questions, I actually think that fact I just said has only come up once in the exam. A long, long time ago. Now, by the way, I wrote down F1 minus F2 equals 6. If you wrote down F2 minus F1, you'd still get the same number, but just a different sign. But that's not really important because V is velocity. So it just means you're saying the sound is going up this way at 306 or it's going down by 306. So that's not a big deal. It's the 306 that you care about.
What do we do if we get the minus one? Can we just write?
Yeah, well, what you're finding is, remember, what does V stand for? Velocity. And what do they ask for? Speed. So you're completely free to just make it a positive. There's no consequence to that. Okay, are we happy with that now?
Yes.
Yep. So we'll go on to the next topic. I think that was the trickiest one from the homework, for sure, but interesting. Okay. Next now. So this is the important one for the exam called Young's double slit experiment. And if you remember last time I showed you with the window how to do it. It's very simple really. A source of light and two screens. There's just one thing I have to say about the light though. Okay, well here I'll just get this back to you. You can move on to that. Okay. If you were doing this in a lab, of course you wouldn't use any light. You'd use it from a machine, like a laser. Okay? So the first thing we have in the experiment is some light source. Now there's a word here. Monochromatic light. Do you know what this means, Carl? Monochromatic?
It's just one color.
Just one color.
And one frequency.
Which means one frequency. So just, if you weren't clear, because I haven't really said it, but just to be clear, when it comes to light, its color depends on the frequency. So if the light is red, the only difference compared to blue light is its frequency, okay? So I think we go red, orange, yellow, green, blue, indigo, violet, and what's happening is as we move up, the frequency is getting higher. And as we move down, the frequency is getting lower. So we usually use red light for this experiment, low frequency. Okay? So that's the first thing. Alright, so let me just get rid of that. You all know the colour. The way you remember this, it's the colours of the rainbow. So that's how you can remember. Okay, so look, I'll leave it doing it red and everything. So we have our red light here. And then this experiment now, I'm making it a little bit different. Well, not a little bit, but I'm just making it a little bit more modern than what Young would have done. Okay, so what we would do in the lab is we use something here that has lots and lots of little slits. It's called a grate, or grating. So on the side, what that looks like is like this. It has lots and lots and lots and lots and lots of really fine slits. So I'll call the letter S the distance between the slits. So if you were to look from above, what's happening, the light comes in and you know it spreads out and it spreads out and it spreads out, and some add together and some cancel. Okay. So by doing the experiment this way, really it just makes it a little bit more precise, a little bit easier to do. The light splits, you get a really bright colour here, that's n equals 0, and then less bright here, and less bright here.
Where n is those.
And n is just a count, just we're counting the dots.
N should be it's 1, not 2.
Oh sorry, I'm not even counting right today. N is 1, n is 2, n is 2. So what's happening is as the light interferes, it adds up. So you could have one dot here, one here, one here, one here, one here. We have an equation that actually relates all of this together. So let's take, for example, this one here, n is 2. Let's call its angle theta.
Angle to what? To n0?
To the second dot. I just drew it to number 2, but it can be to any dot.
No, I mean the angle is between 0 and 2.
Oh, it's between this line here and to the line to 2. Sorry, I should have drawn it there. N lambda equals S sine theta. So that's the formula for Young's experiment. Not very difficult formula, but very useful. So what you got here is theta, of course, is the angle. S is the separation of the slits. Lambda, well, is the wavelength of the light. And n is which dot you want. So what usually happens in this experiment is that you do this and you know the n, you just count. You know the S because it says it on the little card. You know the theta because you can measure the lengths and use your trigonometry. It's the lambda that you usually don't know that you need to work out. Okay? So I'll give you some numbers and you tell me what the wavelength of the light is. So can you write these numbers down, please? I'm going to read them out. You ready to write? So we'll say that let's take the second dot like in my picture. So we look at n equals 2. Now, I won't tell you the theta. All I tell you is the two lengths. Okay? So the length from the screen to the wall is 1 meter. And then from the center dot to the top dot, let's just make that 25 centimeters.
From what?
Yeah, so it's 1 and 25 centimeters. 1 meter and 25 centimeters. What else do I need to give you? The S. And let's say that this has, you looking? 10 slits per 1 millimeter. So it has 10 slits per 1 millimeter. How much is each slit? 0.1 millimeter. Yeah, so just so you know, in the lab and in the exam, they don't tell you, if you look here, just one moment please, this is like the slit, and this is like the slit. This is the S. Okay? They don't tell you how big the S is in the exam or in the lab. What they usually say is how many of these slits you have per millimeter. So in my one, there's 10 of them per millimeter.
So just like
Yeah.
which one was which? The like 1 and 20.
1 and 25 centimeters. 1 meter and 25 centimeters. That's enough information to get the lambda. And I'd like you to do that now for me, and then we'll do it on the board.
10 millimeters per slit. Or 10 slits per millimeter.
Somebody repeat it to him, please.
10 slits per 1 millimeter.
Yes. Joshua, sit properly, please. I think it's affecting your brain.
They would have to give you in meters.
You can actually give it to me if it's really small. Is it really small?
I don't know yet. I need to know if I need to transfer.
The normal thing is to give it in nanometers. But because I made up the numbers, I don't know what it'll be. Does anyone have it yet? Does anyone have it yet? You have it? 9 to minus 5, yeah. It should be really small. In fact, that's roughly similar to what you might get in the exam. I think in the exam they usually have it as micro, maybe. So what's that as micro? How many micrometers is that? Micro is 10 to the minus 6, isn't it? 12.13 micrometers, yeah? Okay, I'm going to do it on the board now. Okay, so lambda equals S sine theta over n. N is 2. S is, I said 10 per millimeter, didn't I? So that's 10 to the minus 3 divided by 10. Multiply sine theta, and the theta was tan inverse 0.25 over 1. Wasn't that right? Yeah. So this is sine, if you want to type it in your calculator in one go, tan inverse a quarter. Okay, and if you type that all in,
So that wants to be 10 over 10 to the minus 3.
this is millimeter divided by 10, so this is a millimeter to the minus 3. Yeah, so yeah, this is right. And what do we get? 12 times 10 to the minus 6 meters. Yeah.
Slits is in centimeter.
No, that's okay. 10 to the minus 3 now is in meters because 1 millimeter is 10 to the minus 3 meters and it's 10 per millimeter. So I mean you could work it out as how many per meter, but I mean it should give you the same answer. Did you do it this way, or are you saying that you think it would be different if you do it with meters?
I thought 10 per millimeter was 10 with 10 to the other way around.
You had it upside down.
Yeah.
No, if you think about it, if I have this distance and I want to know how much it is if there are 10 pieces in the distance, then you divide the distance by 10. So that's it then. So it is 12.13 micrometers. Yeah.
Yes.
Now, if I go back up to the diagram, do you think these distances, these dots are the same distance apart?
No.
Well, what I would like you to do now for me is I want you to tell me, for the same question, what is this distance here? So now this time, I basically want the angle, because if you have the angle, then you can work out the distance. So can you get me this angle here, please? The n is 1, the lambda is the same, the s is the same, but it's the theta that I want now. Okay, so can everybody do this for me, please?
Okay. N is 1.
The n is 1, I want the angle, so you can get the length on the wall. Now please be very, very precise with your calculator, so try to leave all the calculations until the end, like what I did. The lambda is the same, and if you still have it on your calculator, try to use that number. Is the angle. Good. Now keep that on your calculator. You now want the length. So what's the formula? Well, we know the adjacent, and we want the opposite, and we have the angle. So we should use tan. So tan, the angle, is the opposite of the adjacent. But I want the length from 0 to 1. The adjacent is 1. That's nice because then it means tan is opposite over 1. So tan is opposite. So in other words, if you just type tan of the angle on your calculator, you've got the answer. 0.122. Is that half of the previous information I gave you? What did I say the length between 0 and 2 was? And what answer did you get? Yeah. Now, was there any... Almost a half, but not quite, right? So the point I'm trying to make is they're roughly equal distance apart, but they're not exact. That's important for the next formula I'm going to show you. The next formula, you can use it in the exam, and it's accurate, and it's in the formula book. But just so you're clear, if we're being very, very strict, they're not quite the same distance, but they're nearly the same distance, okay? So for this next formula, just keep that in mind. Oh, actually, no. One more part before the next formula. I would now like to know how many dots there are. Now, anybody got any ideas for this? How many dots are there? So for example, look up guys, does that go all the way to n infinity? It might, we don't know. But what's happening with the angle as we move along the wall? It's increasing. But there's some limit at the angle, which is 90. Because when the angle is 90, what happens? Yeah, it doesn't hit the wall then anymore, doesn't it? So in other words, the last dot will have the angle just before 90, right? So what we want to do next is now we make the angle 90, and I want to find the n. And whatever answer we get there, that's the impossible answer, because that's when it's parallel. So we just go to the number before that. Okay? So give me the n now, please. Lambda is the same, s is the same, and then theta is 90. Yes, but I don't think my question. Oh, because it's one in the wavelength, yeah. 8.2.
Somewhere between 8 and 9.
So yes, if you got 8.2, then what's the last dot?
8.
8. So
even if you get 8.9, the last dot is 8.
correct. Even if you got 8.999, the last dot is still 8, because 8.99 or 8.2 is the impossible dot. So if it's 8, how many dots are there in total? 17. Don't forget the 0 in the middle. So this will have 17 dots in the wall. We okay with that? Yep. Okay, so let me give you the second formula now for this. There's only 2. So the second formula is, let's go down here. Lambda equals x s over big D. So there's 2 letters that are new here in this formula, x and big D. But the big D, that's just the distance, focus. That's just the distance from the slit to the wall. Distance to wall. And the x is called the fringe separation. Fringe separation. The distance between the dots on the wall. Okay, so now what I would like everybody to do for me, it's the same question again, and this time I would like you to tell me what the x is. That is, what is the distance between the dots on the wall? What is it?
0.1213.
0.1213 meters. Which isn't really too surprising, because if you think about it, at the start I said, how far was it from the 0 to the second order? It was 25 centimeters, right? So if I divide that by 2, what do I get? 0.125, and what do we have as our answer? 0.1213. So, I mean, it's what you expected to be roughly 12.5 centimeters. Did you all get 0.1213? Yeah? Okay. Actually, let's have a look at the book then. Okay. What page will we on? We did that one. Yeah, okay. So if you were to look at page 40, please, you get 40. You see 40 there? Yes. So you see that they give you the formulas, although they just use different letters. But if you look at the picture on page 40, do you see at the bottom right of page 40? That's what it would look like on the wall. You see that? All the bars. So the two formulas we've used, in fact, they are there in the book, but they use different letters, so it's hard to see. But that's the picture there anyways. So let's have a look at some of the questions. Okay. Okay, this is very long to get to the questions. Okay. Can you go to 63, please? Yeah, this is more like it. I'd like you. No, I just want you to do a couple here to practice, and then we'll go on to more examples I want to do for you. So just to make sure we're all happy, can we do? Let me see. 2 and 3. Question 2 and 3 on page 63. Can you just do that now? And we'll look at more examples. So it's a little bit of revision. Number 2 is about the refractive index, n equals c over v. And then number 3 is about the formulas we're using today. And actually, if I can find a Snell's law as well, but I don't think I can. Double slit. No, there's no Snell's law in this, just the 2. Right, so just do 2 and 3 for me now, please.